Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point and you will not miss a thing. Tonight we are going to talk about black holes, slowly, without hurrying. For much of the 18th century, natural philosophers in Britain worked with an account of light that treated it as a stream of small bodies, thrown out from the surface of a candle or a star, and traveling onward through empty space until they met an eye or a wall. Newton had laid out this view in the optics, and although he was careful about how far he pressed it, the general shape of the picture was plain. Light consisted of corpuscles were matter, and matter obeyed the same laws of motion that governed planets, tides, and cannonballs. A ray became a trajectory. Refraction in glass became a question of forces acting near a surface, and the study of light fell, quite naturally, under the heading of mechanics. That assumption carried a consequence within it, one that took several decades to be written down. Gravity, in the Newtonian scheme, pulls on anything with substance, which meant that a particle of light climbing away from a heavy body would be slowed on its way out, exactly as a stone thrown upward from the ground is slowed and eventually turned back. Throw the stone harder, and it rises further before returning. Throw it hard enough, and it never returns at all. And the speed at which that changeover happens depends on two things only: the mass of the body and the distance from its center to the point where the throw begins. Anyone comfortable with those relations could ask how heavy and how compact a star would have to be for the threshold speed to reach the speed of light. Rough values for that speed were already in circulation, obtained first from the irregular timing of the eclipses of Jupiter's moons, and later confirmed by the slight annual wobble in the apparent positions of stars, a wobble that follows from the motion of the Earth combined with the finite speed at which light crosses the intervening distance. Both methods gave a figure not far from the modern one of close to 300,000 kilometers in each second. Enormous by any terrestrial standard, it was still a finite number, and a finite number can be compared with another. John Michell, rector of the parish of Thornhill in Yorkshire and a Fellow of the Royal Society, made that comparison. He had trained at Cambridge, had written earlier on magnetism and on the causes of earthquakes, and had designed the delicate torsion apparatus that Henry Cavendish would later use to weigh the Earth. Michell published little and lived at some distance from the learned societies of London, corresponding instead with a handful of colleagues, Cavendish among them, and it was Cavendish who read Michell's long paper on the stars aloud to the Royal Society in 1783, after which it appeared in the Philosophical Transactions. The paper was not offered as a piece of speculation about invisible objects. Its stated purpose was practical: to describe a means of finding the distances, sizes, and masses of the fixed stars using the fact that light leaving a heavy star would arrive traveling a little more slowly than light from a lighter one. Working through the arithmetic of that idea took Michell across a range of possible stellar masses, and toward the far end of that range he came upon a case in which the diminution was no longer slight. A star of the same density as the Sun, but with a diameter some 500 times greater, would hold its own light back entirely. Particles emitted from such a surface would rise, slow, stop, and fall again, and none of them would reach a distant observer. Michel stated the result and then, rather than dwelling on its strangeness, went on to consider what could be done about it. If bodies of that kind existed, they would give no light of their own, but they would still pull on whatever lay near them, and their presence might be inferred from the motion of a luminous companion swinging around a center that appeared to hold nothing. Some years earlier, he had argued, on statistical grounds, that pairs of stars found close together on the sky are too numerous to be accidental alignments and must in many cases be genuine partners bound by gravity. Having already accepted that stars orbit one another, he had the means to imagine a partner that could be felt and not seen. He suggested, too, that the slowing of light from very heavy stars might be measured directly, since a beam traveling more slowly should be bent more sharply on passing through a prism, and a careful comparison of one star's light with another's might reveal the difference. Nothing in the instruments of the 1780s could have detected such an effect, and the proposal went untested. Michel died a decade after the paper appeared, and his suggestion about stars whose light cannot escape survived as a few paragraphs in a volume of proceedings that few readers had reason to revisit. Pierre-Simon Laplace arrived at much the same conclusion in France, and set it down briefly in his exposition of the system of the world in 1796. His example used the density of the Earth rather than that of the Sun, and gave a body some 250 times the Sun's diameter as the point at which light would be retained. The arithmetic differs from Michel's only in the choice of starting figures. Laplace called such objects obscure bodies, and remarked that the largest bodies in the universe might therefore be the ones nobody could observe. In later editions of the same work, the passage no longer appears, and it was quietly dropped without any note explaining its removal. What removed the ground beneath the idea was a change in the understanding of light itself. Around the turn of the 19th century, Thomas Young demonstrated that light passing through narrow openings produces patterns of alternating brightness and darkness that make sense only if the light arriving by two different paths can add to or cancel itself, which is behavior proper to waves rather than to particles. Augustin Fresnel then built the wave account into a full mathematical theory, one that handled diffraction, polarization, and the peculiar bright point at the center of a circular shadow, a prediction that had been raised as an objection to the theory and was then found in the laboratory. By the 1820s, the wave picture had carried the field. A wave in the ether, as it was then conceived, had no mass and no clear reason to answer to gravity at all. Waves travel at a speed set by the medium they move through, not by the vigor with which they were launched. So the whole framework of throwing something upward and asking whether it comes back no longer applied. The question that Michel and Laplace had posed did not receive an answer. It simply lost the language in which it had been asked, and there was no obvious way to put it again. Their dark stars, in any case, were not quite the objects that later physics would describe. A body that holds its own light back by Newtonian gravity still has a surface, still has an interior in which nothing very unusual happens, and still lets light rise some distance before falling again, so a nearby observer would see it perfectly well. Someone standing on such a star could climb away from it slowly, hauled up by a rope, since the threshold speed applies only to a projectile given one push at the start. Nothing in the 18th century version forbids escape, and nothing in it points toward a boundary that can be crossed in one direction alone. Even so, the arithmetic left a curious residue. If the escape speed condition is written out in the Newtonian way, using the mass of the body and the speed of light, it yields a particular radius, and that radius turns out to be numerically identical to the one that would emerge more than a century later from a very different theory of gravity, in which space and time are curved and light follows the curvature. Two incompatible accounts of the world, arriving at the same figure by unrelated routes, which is the sort of coincidence that tends to be noticed only in retrospect. Through the rest of the 19th century, astronomy had a great deal else to occupy it, including the first measurements of stellar distances by parallax, the sorting of starlight into spectra, and the slow accumulation of catalogues and photometry. The stars whose light could not leave them were not disproved, nor argued over, nor even much mentioned. They were set aside, in the way that a question is set aside when the tools for asking it have been replaced by better tools that happen not to fit. Gravitation was recast in the second decade of the 20th century by a line of reasoning that began with a very ordinary observation about falling. A person who steps off a ledge, or a workman who slips from a roof, does not feel heavy on the way down. Weight vanishes while the fall lasts, and everything released at the same moment falls alongside, keeping station, as though gravity had been switched off. Albert Einstein, then employed in the patent office at Bern, and thinking about these matters in whatever hours the work left him, took that everyday fact and treated it as a principle rather than a curiosity. Inside a small enough region, falling freely, there is no experiment that distinguishes gravity from no gravity at all, and equally, in a sealed room, accelerating steadily through empty space, there is no experiment that distinguishes acceleration from weight. From that starting point, the consequences accumulated in an order that could not easily be stopped. If gravity is locally equivalent to acceleration, then light must be bent by it, since a beam crossing an accelerating room arrives lower on the far wall than it started. Clocks at different heights in a gravitational field must run at different rates, the lower ones more slowly, because a signal climbing away from a mass arrives with its vibrations stretched. And once the rates of clocks and the lengths of rulers depend on where they are placed, the flat geometry that Euclid had described and that Newton had assumed can no longer be the geometry of the world. Straight lines and fixed distances become approximations valid in small patches, as a flat map is a fair approximation of a small district and a poor one for a hemisphere. 8 years separated the first sketch of that argument from a finished theory, and much of the delay lay in mathematics rather than physics. The tools needed already existed, having been developed for their own sake during the previous century by geometers studying curved surfaces and the properties that survive a change of coordinates. Einstein learned them with the help of his old classmate Marcel Grossmann, who knew the literature of differential geometry and pointed him toward the calculus of tensors, a notation designed precisely so that statements written in it hold whatever coordinate labels are used. The going was slow, with several wrong turns and one field theory abandoned after 2 years of work, and the final version arrived only after a period of intense recalculation in the autumn of 1915. In late November of that year, Einstein presented the field equations to the Prussian Academy of Sciences in Berlin. Their content can be stated in a sentence, though solving them is another matter. The curvature of spacetime at any place is determined by the energy, momentum, and pressure of whatever is there. Matter tells geometry how to bend, and geometry tells matter how to move. because a body under no force other than gravity travels along the straightest available path through the curved arrangement, which is called a geodesic. Gravity, in this account, is not a pull transmitted across a gap. Planets orbit for the same reason that two travelers walking due north from different points on the equator find themselves converging, not because a force draws them together, but because the surface they are crossing is shaped that way. Two older puzzles settled themselves almost immediately. Mercury's orbit had long been known to turn slowly in its own plane, and after every known perturbation from the other planets had been accounted for, a residue of about 43 seconds of arc per century remained unexplained, a discrepancy that had prompted searches for an undiscovered inner planet. The new equations produced that residue without adjustment. They also predicted that starlight grazing the edge of the Sun would be deflected by roughly 1 3/4 seconds of arc, twice what a Newtonian treatment of light as falling particles would give, and eclipse expeditions in 1919. Observing from Brazil and from an island off the coast of West Africa reported deflections closer to the larger figure than the smaller. That result carried the theory out of the journals and into the newspapers. The field equations, however, are not friendly to exact solution. They are 10-coupled equations, non-linear, since the curvature contributes to the energy that generates curvature, and Einstein had obtained his early results with an approximation scheme suited to weak fields, treating the deviation from flatness as a small correction. He expected that exact solutions, if any could be found, would take years of effort and would probably require considerable simplification of the physics. The expectation lasted a matter of weeks. Karl Schwarzschild was, by then, one of the more accomplished figures in German astronomy, director of the Astrophysical Observatory at Potsdam, with published work spanning photographic photometry, the transfer of radiation through stellar atmospheres, and the statistics of stellar motions. He had volunteered for military service in 1914, in his early 40s, and after postings in Belgium and France, he was serving on the Eastern Front, where his duties involved calculations of trajectories for artillery. Copies of Einstein's Academy papers reached him there. Within a short time, he had worked out the exact geometry of spacetime around a single spherical mass sitting alone in empty space, static and without rotation, which is the closest idealization relativity offers to an isolated star or planet. His letter reached Einstein at the end of December 1915, and Einstein, who replied that he had not expected the problem to yield so simply, presented the paper to the Academy in January of the following year. A second paper followed within weeks, treating the interior of a sphere of incompressible fluid and joining that solution to the exterior one at the surface. Schwarzschild did not live to see the theory tested. He had contracted a painful autoimmune disease of the skin called pemphigus, which was untreatable at the time, and he was invalided home and died in May 1916 at the age of 42. The same exterior geometry was derived independently and at nearly the same time by Johannes Droste, a doctoral student of Hendrik Lorentz in Leiden, whose paper appeared later in that year, and whose derivation was, in some respects, the cleaner of the two. What the solution describes is straightforward at a distance and strange close in. Far from the mass, it reduces to Newton's inverse square law with small corrections, and those corrections account for Mercury's drifting perihelion and the bending of starlight. Nearer the center, The geometry departs from the flat case in two linked ways. Clocks tick more slowly the deeper they sit, and radial distances measured with rulers exceed what the change in circumference would suggest, so that a shell drawn around the mass encloses more depth than a flat reckoning allows. Everything depends on the total mass and on nothing else. A feature later proved to be general for spherical symmetry in vacuum, so that a pulsating spherical star produces exactly the same external field as a static one of equal mass. Something went wrong, though, at one particular radius. In the coordinates Schwarzschild used, one term of the metric grew without limit there, while another fell to zero, and the mathematics ceased to give sensible answers. That radius depends only on the mass, being twice the gravitational constant times the mass divided by the square of the speed of light, and for ordinary bodies it lies absurdly far inside them, about 3 kilometers for the mass of the Sun, whose actual radius is near 700,000 kilometers, and about 9 millimeters for the mass of the Earth. Since the exterior solution applies only outside the matter, and since no known object came close to being that compact, the troublesome surface sat in a region where the equations did not describe anything in the first place. It was, for practical astronomy, a place that did not exist. Through the 1920s and into the 1930s, the surface kept the name Schwarzschild singularity, and the general assumption was that it marked either a genuine breakdown of physics or an idealization too extreme to be taken seriously. Arthur Eddington, in 1924, wrote down a change of coordinates in which the misbehavior disappeared, though he made little of the point at the time. Georges Lemaitre, the Belgian priest and cosmologist, stated the matter plainly in 1932. The trouble was in the coordinates and not in the geometry, and an observer falling freely inward would notice nothing peculiar on crossing. Curvature there is finite. Only the labels fail. Whether matter could ever actually be compressed within that radius was not a question relativity alone could answer, since it depended on what holds a star up against its own weight, and on whether that support has a limit. Those questions belong to the people studying the insides of stars, and they were, at that moment, arriving at answers of their own. Sirius, the brightest star in the night sky, had been suspected since the 1840s of carrying something unseen along with it, because Friedrich Bessel found that its path across the sky wavered slightly, as though it were being tugged by a companion too faint to see. In 1862, the American telescope maker Alvan Graham Clark, testing a new lens, caught sight of the companion as a dim point beside the glare. For half a century, it was assumed to be a small, cool, exhausted star. Then, in 1915, Walter Adams at Mount Wilson obtained a spectrum of it and found the light was not the reddish glow of a cooling ember, but the white light of a hot surface, which meant that a star radiating so little, while being so hot, had to be tiny, a body roughly the size of the Earth, carrying something close to the mass of the Sunday. That conclusion produced a density no laboratory had ever approached, and Arthur Eddington, who was then building the modern theory of what goes on inside a star, treated it as a genuine difficulty, rather than an error of measurement. His account of stellar interiors, worked out through the 1920s, described a star as a sphere of gas in which the outward push of pressure balances the inward pull of weight at every depth, with heat flowing steadily outward from a hot core. Applied to the companion of Sirius, that picture broke down. Matter compressed 100,000 times beyond ordinary solids could not behave as an ordinary gas. And worse, a star of that kind seemed to have no dignified way to die, since it had already spent its nuclear fuel and yet would need to supply energy in order to expand back to a normal size as it cooled. The escape came from the new quantum theory, and it came quickly. Wolfgang Pauli had stated in 1925 that no two electrons may occupy the same quantum state, and in the following year, Enrico Fermi and Paul Dirac worked out the statistical behavior of particles obeying that rule. Ralph Fowler, in Cambridge, saw within months what this meant for dense matter. In a white dwarf, the atoms are crushed until their electrons are no longer bound to individual nuclei but form a common sea, and the exclusion principle forbids that sea from settling quietly into its lowest states. The electrons are forced to occupy higher and higher levels of motion simply because the lower ones are already taken, and the resulting pressure has nothing to do with heat. Such a star could cool forever without shrinking away, because what held it up would not cool with it. Physicists call that condition degeneracy, and its defining feature is that the supporting pressure depends on density alone. Squeeze the material, and the electrons are confined to smaller volumes, which by the uncertainty relation obliges them to carry larger momenta, which in turn stiffens the resistance. Fowler's calculations seem to settle the fate of white dwarfs, and for a few years it did. A cooling star of modest mass would end as a dark, dense, quantum-supported sphere, stable indefinitely, requiring nothing further to explain it. Within a few years, though, the picture acquired a limit. Edmund Stoner in Leeds and Wilhelm Anderson in Tartu each examined what happens when the electrons in the degenerate sea are pushed to speeds approaching that of light as the density climbs, and both found that the pressure then rises more slowly with compression than the simple treatment had assumed. Momentum can grow without bound, but speed cannot, and it is speed that determines how often the particles deliver their push. The stiffness of the material therefore softens exactly where it is most needed, and the softening implies that above a certain mass, no equilibrium exists at all. Subramanian Chandra Sekhar, 19 years old and traveling by ship from Madras to England to begin research at Cambridge, carried out his own version of the calculation during the voyage in 1930. He treated the relativistic degenerate gas properly and solved the resulting structure equations. And the answer was a definite ceiling. A white dwarf could exist only below a particular mass, a value that depends on the composition of the material and works out, for the compositions later thought appropriate, at a little under 1.5 times the mass of the Sunday. Above it, the star's own weight would overcome anything the electrons could supply. Behind the number lies a matter of scaling that makes it unusually clean. When the electrons are slow, pressure varies roughly as the 5/3 power of density, and the star can always find a size where support and weight agree. When they become relativistic, the exponent drops to 4/3, which is precisely the way the star's own gravity scales with compression, so the two effects change in step and the balance becomes indifferent. At that point, the mass, and not the radius, decides the outcome, and the mass that permits equilibrium at all is fixed by fundamental constants alone. Reception of the result was not warm. Eddington, whose standing in British astronomy was considerable, rejected the relativistic treatment of the degenerate gas as an illegitimate mixture of theories, and said so at a meeting of the Royal Astronomical Society in London in January of 1935, immediately after Chandrasekhar had presented his work, arguing that nature would surely not permit a star to behave in so absurd a manner. Several physicists on the continent, among them Niels Bohr and Leon Rosenfeld, privately assured Chandrasekhar that his derivation was correct, but none took up the argument in public, and the disagreement was never formally resolved, so much as outlived. Chandrasekhar set the problem aside, moved to the Yerkes Observatory in the United States in 1937, gathered his stellar structure work into a textbook published in 1939, and turned to other subjects for a while. The limiting mass eventually took his name, and much later, in 1983, the work was recognized with a share of the Nobel Prize in Physics. Lev Landau, working in the Soviet Union, arrived at a comparable limit independently and published it in 1932, drawing from it a conclusion he stated more bluntly than most. For masses above the threshold, the laws of quantum mechanics, as then understood, offered nothing that could stop a contraction. He was inclined to suspect that the laws themselves failed at such densities, rather than that the contraction was real, which was a common instinct at the time. Everything shifted again in the same year, when James Chadwick identified the neutron in Cambridge and gave physics a heavy, uncharged particle that could be packed far more tightly than electrons and protons in an atom. Walter Baade and Fritz Zwicky at Caltech proposed in 1934 that the exceptionally bright stellar explosions they had begun to catalogue, and for which they coined the term supernova, marked the transformation of an ordinary star into a body composed almost entirely of neutrons, extraordinarily small and extraordinarily dense. Such an object would be supported in the same way as a white dwarf by degeneracy, but with neutrons in the role of the electrons, and since neutrons are nearly 2,000 times heavier, the equilibrium radius shrinks to a scale of some kilometers rather than thousands of them. The same logic that produced a ceiling for white dwarfs applied again. Richard Tolman worked on the general relativistic equations of equilibrium, and in 1939 Robert Oppenheimer and George Volkoff at Berkeley solved them for a sphere of degenerate neutrons, finding a maximum mass of roughly 7/10 of a solar mass for the assumptions they made. In relativity, the accounting is harsher than in Newtonian physics, because pressure itself carries energy and therefore gravitates, so that the very thing resisting collapse adds a little to the weight it must resist. Oppenheimer and Volkoff were careful to note that their neutrons were treated as a non-interacting gas, and that nuclear forces, then barely understood, would change the answer, most likely upward. What remained by the end of the 1930s was a gap with nothing in it. A stellar core below the first limit could rest as a white dwarf, one below the second could rest as a ball of neutrons, and above these values the known sources of support were exhausted, with no third form of matter waiting in reserve. Whether a heavy core might shed enough mass on the way down to squeeze under a limit was an open question, and one that could not be settled by counting equilibria, since the answer depended on following the material inward as it fell. Following a star inward, rather than asking where it might finally come to rest, called for a different sort of calculation, one in which the geometry itself changed from moment to moment and the matter inside it was in motion the whole while. Equilibrium problems are, in their way, the simpler kind, since one sets the inward pull against the outward push, and either finds a balance or fails to find one. A collapse offers no balance to solve for. It has a history instead, and the equations must be carried forward through that history, tracking the field outside the falling material and the conditions within it, with the two joined at a boundary that will not hold still. Richard Tolman had published, in 1934, a general treatment of spherically symmetric distributions of pressureless matter in the relativistic theory, and that gave later workers something to build on. To make the problem tractable at all, the assumptions had to be unsparing. The collapsing body was taken to be exactly spherical, so that no direction was singled out, and no gravitational waves could carry energy away. It was given no rotation. Its density was held uniform from center to surface, and its pressure was set to zero, so that every element of matter simply fell freely under the gravity of whatever lay inside it. Actual stellar cores answer to none of these conditions. The justification offered was that pressure, under relativistic accounting, adds to the gravitating mass even as it pushes outward. So a model with no pressure at all was unlikely to be falling faster than a real core would, which meant the calculation was not exaggerating what it described. Oppenheimer, having finished with maximum masses, took up the falling case together with a graduate student named Hartland Snyder, and their paper reached the Physical Review in the opening days of September 1939, a week in which few people anywhere were reading physics journals. A closely related solution had appeared the year before, in a German periodical from the Indian physicist B. Dat, and went almost unread. Neither treatment ran long. The mathematics is compact, the conclusions are set down without ornament, and the phrase black hole appears in neither, since it would not come into use for close to 3 decades. Seen from within, the process is brisk and, in its local details, unremarkable. A clock carried along with the falling matter records a finite and rather short interval, minutes rather than ages, for material beginning its fall from the dimensions of a dense stellar core, and well under an hour for a body the size of an ordinary star. Nothing in the immediate physics marks the moment at which the surface passes the particular radius that Schwarzschild's solution had picked out. The matter is in free fall, weightless, its surroundings behaving as the surroundings of any freely falling thing behave, and it keeps going inward, the density climbing without bound as the whole distribution draws together toward the center. Traced instead by an observer who stays far away and watches, the same collapse never comes to an end. In the time coordinate natural to that distant vantage, the shrinking surface creeps toward the critical radius and slows as it approaches, its rate of contraction dwindling so that the arrival is always still to come. The star does not bounce, and it does not settle into a new equilibrium. It hangs, apparently suspended, at a size very slightly larger than the radius it is asymptotically approaching. 2 accounts of one event, then both correct, and the difference between them was the substance of what Oppenheimer and Snyder had found. Light carries the outside account, and light is what the geometry acts upon. Each successive crest leaving the receding surface has a longer and more difficult climb than the crest before it. So the signal reaching a distant telescope is stretched toward longer wavelengths, its arrivals spaced further and further apart, and its brightness dropping away exponentially. The characteristic time of that fading is set by how long light needs to cross the gravitational radius itself, which for a few solar masses comes to a few hundredths of a thousandth of a second. So the suspension that lasts forever in the coordinates belongs to an object that goes dark, for any practical purpose, at once, leaving behind only the gravitational field it had already established. No contradiction lives in this pair of descriptions, though it took a long while for that to be generally accepted. The unending duration belongs to a particular scheme for labeling events, the coordinates in which the original exterior solution had been written, and those labels lose their usefulness precisely at the radius in question, in much the way that lines of longitude crowd together and cease to be helpful at a pole. Georges Lemaitre had pointed out in the early 1930s that the trouble at that radius was a defect of the description rather than of the geometry, and the Oppenheimer and Snyder calculation, which followed the matter in its own frame, showed the same thing from the other side, but the lesson was absorbed slowly, and for 2 decades the frozen appearance was often mistaken for the whole story. Few readers were persuaded that any of this described a real fate for real stars. Einstein published in that same year an argument that a system of gravitating masses could never be squeezed inside the critical radius, so the question would not arise in nature. The reasoning rested on conditions the collapsing case did not satisfy, yet the reluctance behind it was widely shared. Eddington had made his own distaste plain years before in the dispute over the white dwarf limit, holding that some provision of physical law ought to spare a star from shrinking indefinitely. Astronomers, for their part, had spectra and colors and catalogues to attend to, and a body that removed itself from view within a fraction of a millisecond offered them nothing to measure. What the paper did not claim is as instructive as what it did. Uniform density, perfect sphericity, and the absence of pressure and rotation were acknowledged as conveniences, and whether a lumpy, spinning, pressurized core would also converge on a point of unbounded density rather than missing the center and passing through into some other configuration remained entirely open, nor was there any account of what the resulting object would look like to a theory of matter at densities beyond anything laboratory physics could reach. These questions were not idle, and they would not be settled by continuing along the same lines. They needed mathematical tools in the study of geometry in the large that did not yet exist. The war then took the participants elsewhere. Oppenheimer's attention moved to fission and then to the weapons project, and he never returned to gravitational collapse in print. Snyder went on to work on the design of particle accelerators. Volkoff turned to other problems. The subject itself thinned out for the better part of 20 years, sustained by a small number of relativists working largely apart from astronomy, while the questions that had produced it, the fate of a heavy core and the meaning of the critical radius, stayed on the shelf. Later, assessments have tended to treat those few pages as the first description of what collapse actually does, arrived at with the sparest possible model, and stated in language free of any suggestion that the authors thought they were describing something exotic. The freezing at the surface, understood properly, is a statement about which events can send light to which observers, and in that sense the paper of 1939 already contained the one-way surface that a later vocabulary would name, without quite recognizing that it had it in hand. Midway through the 1950s, general relativity was a small and rather isolated subject, taught in a handful of departments, admired for its mathematical form, and tied to observation by only a few modest tests. A meeting held at Chapel Hill in North Carolina at the start of 1957 brought together most of the people then working on it, and among the matters resolved there, at least to the satisfaction of those in the room, was whether gravitational waves carry energy in any physical sense. Feynman's argument that a passing wave would slide a bead along a rod and that friction between bead and rod would then produce heat made the case in a form that was difficult to dispute. Historians of the field have often treated that gathering as the point at which the temper of the subject shifted, the equations being asked less about their formal elegance and more about what they predicted would actually happen to matter left to its own gravity. Coordinates were part of what had made the critical radius so hard to interpret. In the form Schwarzschild had written the metric, one term diverges at that radius while another falls to zero, and for decades this misbehavior was read as a sign that something physically violent occurred there. Lemaitre had argued in the early 1930s that the trouble lay in the description rather than in the underlying geometry, since a freely falling observer would notice nothing peculiar in passing through. And in 1958, Finkelstein presented a coordinate system in which the surface showed itself plainly as what he called a one-way membrane, a boundary crossable inward and not outward. Kruskal, and independently Sekeres, supplied the fullest extension of the geometry in coordinates covering all of it at once, and Penrose devised a method of drawing such spacetimes on a finite diagram in which light rays travel at fixed angles, so that questions about what can influence what could be answered by inspection. Rotation was the ingredient still absent from every exact solution in hand. Stars spin, and a shrinking core would spin faster as it contracted. So a perfectly static description could only ever be an idealization of the real problem. In 1963, Roy Kerr, a New Zealand mathematician then working in Texas, published a short paper giving the field around a spinning mass, arrived at while classifying metrics according to an algebraic property of their curvature rather than by attacking collapse head-on. He presented the result at the first of the Texas Symposia on Relativistic Astrophysics, convened in Dallas that December, where its importance was not widely appreciated by an audience preoccupied with the newly identified quasars. The Kerr geometry carries features the spherical case lacks: an outer horizon and an inner one, a surrounding region in which no observer can remain at rest with respect to the distant stars, and a singularity shaped like a ring rather than a point. A version carrying electric charge as well as spin appeared within 2 years, and with that, the catalogue of stationary solutions looked closed. Whether it was closed in the stronger sense that no other stationary possibilities existed at all, occupied another decade. Israel proved in 1967 that a static, uncharged, regular horizon in vacuum had to be the spherical one. Carter and Hawking, and later Robinson, pushed the argument into the rotating case, with the consequence that a collapsed object, which has finished settling, can be labeled by its mass, its angular momentum, and its charge, and by nothing further. Every other property the original star possessed, its chemical composition, its magnetic field, its surface irregularities, its history, either falls within the horizon or is carried off by radiation. Price worked out how the shedding proceeds, each higher lump in an external field decaying at its own rate as waves stream away. Wheeler's summary of the conclusion, that a black hole has no hair, proved catchy enough that the theorems behind it are still generally cited under that name. Penrose's paper of 1965 altered what could be established about collapse in general. Instead of assuming spherical symmetry, as the 1939 calculation had, he introduced the trapped surface, a closed surface curved so strongly that both the outgoing and the ingoing families of light rays leaving it are converging, and demonstrated that once such a surface exists in a space-time obeying reasonable requirements on its matter content, the geometry cannot be continued without limit. Some paths through it terminate after a finite lapse of time measured along them. Hawking reversed the reasoning and applied it to an expanding universe, running the logic backwards toward the beginning, and the two of them produced jointly in 1970 theorem, covering both situations under weaker assumptions. Singularities, on this account, were not an artifact of an unrealistically tidy model but generic. Penrose additionally suggested, in 1969, that such singularities would always be concealed behind horizons and never exposed to distant view, a conjecture that has resisted both proof and clear refutation and still functions as a working assumption. Stability formed a separate line of inquiry, and not an idle one, since a solution that disintegrated under the slightest disturbance would describe nothing that could persist. Reggie and Wheeler had begun the analysis of small perturbations of the spherical geometry in the late 1950s, and the calculations were extended through the following decade, yielding the result that a disturbed horizon rings. The disturbance departs as gravitational waves at a discrete set of frequencies determined by mass and spin alone, dying away over a characteristic interval. Vishveshwara exhibited this behavior by numerically scattering pulses of radiation off the geometry. The frequencies acquired the name quasi-normal modes, and their dependence on so few parameters made them, in principle, a means of identifying whatever had produced them. Vocabulary lagged behind the mathematics. Through the 50s and the early 60s, the object was called a collapsed star, or a frozen star among Soviet relativists, who stress the external view in which infall appears to halt, or simply the Schwarzschild singularity, a phrase whose ambiguity caused real confusion. The compact term seems to have circulated in conversation at conferences before anyone committed it to print. A weekly science news bulletin of 1964, reporting a session of the American Association for the Advancement of Science, carried it. Wheeler took it up after hearing it offered from the audience at a lecture in 1967, having earlier been among those most skeptical that complete collapse could occur at all, and his use of it in a published article the following year established it. A few colleagues thought it undignified, and in some languages the literal translation carried associations that slowed its adoption. Yet within a handful of years, no one needed the phrase explained. Hawking's demonstration in 1971 that the combined area of horizons cannot decrease in any classical process handed the subject a quantity behaving strangely like entropy, always increasing, never returned. Penrose had shown 2 years before that energy can be drawn out of a spinning hole by a particle that breaks apart within the rotating zone outside the horizon, one fragment falling in on a retrograde path while the other escapes carrying more energy than the pair started with, and Christodoulou identified the portion of the mass that no such process can reach, the part bound up with the area itself. Bardeen, Carter, and Hawking laid out in 1973 a set of laws for these objects modeled clause by clause on the laws of thermodynamics, with surface gravity standing in for temperature, while cautioning that the correspondence was formal only. Bekenstein, then a graduate student at Princeton, took the opposite position and argued that the entropy was genuine and proportional to the horizon's area. By the early 1970s, the field had textbooks, summer schools, and an agreed core of results. A thick treatise by Misner, Thorne, and Wheeler appeared in 1973. A session at Lay Hausch the previous year had assembled much of the working community in one place for weeks at a stretch. Nearly all of it had been accomplished with pencil, paper, and a little computing. In Princeton, Cambridge, Moscow, and a scattering of other centers, and it concerned objects whose existence remained unconfirmed. What the relativists had assembled, though, was a body of predictions specific enough to be checked against the sky, a family of geometries fixed by 2 or 3 numbers, an upper limit on how efficiently infalling matter could be converted into radiation, a ringing signature with calculable frequencies, and a shadow of definite angular size for a whole of given mass and distance. The theory stood in that condition, unverified in nearly every particular and no longer in the least vague. Anatomy is an unusual word for an object that contains no matter in the ordinary sense, and yet the region around a collapsed body has definite structure, with surfaces at fixed distances from the center where the behavior of light changes in ways that can be stated exactly. All those distances follow from a single length proportional to the mass, which for a body of 1 solar mass works out at about 3 kilometers, and for the Earth at roughly 9 millimeters. Double the mass and every feature doubles its radius, while the proportions among them stay fixed. That scaling is the reason a whole of several million solar masses is not merely a stronger version of a stellar one, since the same geometry spread across a wider region presents very different conditions at the places a visitor would actually encounter. Nothing marks the horizon locally. It is not a shell of material. No instrument carried through it registers a crossing, and around a sufficiently large hole, the curvature at that radius is mild enough for a body to pass without strain. What sets the surface apart concerns the directions available to light. Near a compact mass, the paths open to a flash are tilted inward, and at one particular distance the tilt becomes total, so that a ray aimed straight outward makes no headway and hovers at the same radius indefinitely. Deeper than that, every path leads further in. Relativists define the boundary accordingly. It encloses the region from which no signal ever reaches a distant observer, however long that observer is willing to wait. Because the definition refers to the whole of the future, the position of the boundary at any given moment depends on what will later fall in. A hole about to receive a large parcel of gas already has its horizon swelling outward to meet the gas, expanding before any of it arrives, since the rays that will eventually fail to escape are precisely the ones tracing the edge. For practical calculation, physicists use other surfaces defined by conditions measurable on the spot, and in quiet circumstances, the two descriptions coincide closely enough. Their disagreement becomes visible mainly during mergers and periods of rapid growth, when the global boundary runs ahead of the local one for a time and then settles back into agreement. Seen from far away, a clock lowered slowly toward that radius runs late, and the discrepancy grows without limit as the clock approaches. Light climbing out of the well loses energy on the way, arriving reddened, so a lamp held near the surface fades toward the infrared and then out of any detector's reach. The rate of that fading is set by the time light takes to cross the hole, which for a stellar mass object is a small fraction of a millisecond, so an infalling lantern would vanish from view almost at once rather than lingering as a visible smear. The older literature spoke of a frozen star for this reason, since the outside record of the fall never quite completes. A clock carried inward tells the other half of the story. Its own reading advances normally, second by second, through the descent and across the boundary, with no jolt and no flash to mark the passage. The traveler loses the ability to send anything back, and loses it without noticing, because the failure of a signal to arrive is a fact about the distant recipient rather than about the sender. Nothing in the local surroundings announces that the last opportunity to turn round has gone. This split between the two accounts, an unfinished fall from outside and a completed one from within, was already implicit in the calculations of the late 1930s, and it remains the single feature of the geometry that most often causes confusion. At 1.5 times the horizon radius of a non-rotating hole lies a surface where light itself can circle. A ray launched exactly sideways at that distance returns to its starting point, though the orbit is unstable, so the slightest inward or outward nudge sends the ray spiraling into the hole or off toward infinity. Rays passing near this radius from outside can loop once or several times before escaping, which means a distant telescope receives, alongside the direct image of whatever surrounds the hole, faint repeated images formed by light that went most of the way around. The bending also fixes the size of the dark patch a hole casts against a bright background, a circle roughly 5 times the diameter of the horizon itself, larger than the horizon because the paths that end on it are drawn inward from a wider catchment. Matter, unlike light, cannot orbit arbitrarily close. For a static hole, the innermost stable circular orbit sits at 3 times the horizon radius, and gas drifting inside it spirals in within a few orbital periods rather than settling. This limit governs how much energy an accretion disk can radiate, since a parcel of gas gives up gravitational energy as it works its way down through the disk and then carries the remainder across the boundary unspent. For a hole with no spin, the fraction released amounts to a few % of the rest mass, several times what nuclear fusion extracts from hydrogen, and the figure rises substantially when the hole rotates rapidly and the last stable orbit moves closer in. Rotation adds a further surface outside the horizon. A spinning mass drags the surrounding geometry around with it, so that free-falling observers acquire angular motion in the direction of the spin whether or not they began with any, and close enough to a rapidly turning hole, this dragging becomes unavoidable. Within a region called the ergosphere, no observer can remain at rest with respect to the distant stars, however powerful the engines, because holding still would require moving faster than light relative to the local geometry. The ergosphere touches the horizon at the poles and bulges outward at the equator, and it is the zone in which energy can be taken from the hole's rotation by particles or by magnetic fields threading the flow. Angular momentum also alters the sizes of everything else. As the spin increases, the horizon of a hole of fixed mass shrinks, reaching half its non-rotating radius in the extreme case, while the prograde stable orbit for matter descends until it nearly grazes the surface and the retrograde one retreats. The family of solutions stops at a definite maximum spin for each mass. Beyond it, the equations no longer describe a horizon at all, and the accepted view is that no physical process manages to push a hole past that value, since matter carrying enough angular momentum to do so is deflected before it can be swallowed. Falling bodies are stretched by the difference in gravitational pull across their own length, and that difference grows as the inverse cube of the distance, while the horizon radius grows only in proportion to the mass. The two effects together mean that the tidal gradient at the horizon weakens as the square of the mass rises. Around a hole of a few solar masses, a human-sized body would be drawn out lengthwise and squeezed sideways past the point of survival while still well outside the boundary. Around one of several million solar masses, the same body would cross the horizon, feeling almost nothing, with the stretching becoming severe only much later, deep inside, when no report of it could be sent out. Within the horizon, the roles of the radial direction and of time exchange places in the mathematics. Moving towards smaller radius becomes as unavoidable as moving toward the future, so the center is better described as a moment lying ahead than as a place lying below. And no amount of thrust postpones arrival by more than a little. The interval available is short and firmly bounded, a matter of microseconds for a stellar mass hole, and of tens of seconds for one of a few million solar masses. Curvature climbs steeply along the way, and in the classical solution, it grows without bound at the endpoint. That unbounded growth is generally read as a statement about the limits of the theory rather than about the world. General relativity, applied to its own solutions, predicts conditions under which its assumptions cease to hold, and a quantum description of gravity is expected to replace the final stage with something finite and different in kind. The rotating solution complicates matters further, since its interior contains a second horizon and mathematical continuations beyond, which most workers regard as unphysical because that inner surface appears unstable to any radiation falling in from outside. What survives all these qualifications is the exterior, fixed by mass, spin, and charge, and testable in every particular from a safe distance. Almost none of the X-ray light arriving at the Earth reaches the ground. Air absorbs those wavelengths thoroughly, so an instrument built to register them has to be carried above the bulk of the atmosphere. And until rockets became available for scientific payloads, there was no way to examine the sky in that band at all. Detectors flown in the late 1940s confirmed that the Sun gives off X-rays, which followed from the temperature of its outer layers, and the quantity turned out to be modest. Scaling that output to the distance of even a neighboring star yielded a signal so slight that few astronomers thought an X-ray sky beyond the solar system worth the effort of hunting for. An Evaporation rocket flight in 1962 carried 3 gas-filled counters with a wide acceptance angle, and its stated aim was to look for X-rays fluorescing from the lunar surface under sunlight. The counters registered something other than the moon. As the rocket turned on its axis and swept its detectors across the sky, they recorded a strong source in the direction of Scorpius, along with a diffuse glow spread over the whole field that belonged to no particular object. Neither finding matched what the theory of stellar atmospheres would have predicted, since the Scorpius source, if it lay at a plausible distance within the galaxy, was pouring out X-rays thousands of times more freely than the Sun releases energy of every kind combined. Sources located in the surveys that followed were labeled by constellation and by order of detection within it, and so the first strong one in Cygnus became Cygnus X1, when rocket instruments picked it out in the middle of the decade. Those flights were brief affairs. A sounding rocket gave perhaps 5 minutes above the absorbing layers. The counters had no focusing optics, and a position could be narrowed only by masking the detector with a collimator and noting when the signal rose and fell as the payload rotated. Error regions came out a degree or more across, and a patch of that size along the band of the Milky Way holds many thousands of stars, any of which might or might not have been responsible. Satellite observation changed the arithmetic of the problem by replacing minutes with years. On the 12th of December, 1970, a small spacecraft dedicated wholly to X-ray astronomy was launched from a platform anchored off the coast of Kenya, on the anniversary of that country's independence, and it was given the Swahili name Uhuru, meaning freedom. Turning slowly about its axis, with proportional counters looking out through honeycomb collimators, it worked its way across the entire sky and returned a catalogue running to several hundred entries. Many of the strong galactic sources prove to sit in binary systems, where a compact body draws material from an ordinary star and heats it in the process. Centaurus 10.3 supplied the clearest early example of how such a system could be read. Its X-rays pulsed every few seconds, with a strict regularity that pointed to a magnetized, spinning object channeling infalling gas onto small patches of its surface, and the pulses vanished at regular intervals as that object passed behind its companion. Rotation of a solid body and eclipses by a star together meant a neutron star in orbit. The interpretation was welcome rather than surprising, since neutron stars had already been established by the discovery of radio pulsars, and it gave the whole field a working template against which any less obliging source could be compared. Cygnus X1 refused to fit that template in 2 respects. Nothing in its output repeated in the manner of a rotating body, and instead of steady emission punctuated by pulses, it flickered continuously, with substantial changes in brightness occurring on timescales shorter than a second. Rapid variation puts a ceiling on size, because a region cannot brighten coherently much faster than light crosses it, and 1/10 of a second corresponds to some 30,000 kilometers. The emitting zone was therefore comparable to the Earth in scale, or smaller, while radiating at a rate that would take an ordinary star's entire surface to match. Fixing the source's position closely enough to identify it optically fell to radio astronomers. In 1971, 2 groups independently found a weak radio source in the region, appearing at the same time as a marked change in the X-ray behavior of Cygnus X1, and radio techniques could give a position accurate to about a second of arc. That position coincided with a 9th magnitude blue supergiant, a hot star of late O type known only by a catalogue number from an extension of an older survey of stellar spectra. Sitting some 7,000 light-years away, it is a heavy, luminous star nearing the end of a short life, and it shows no sign of being disturbed in any obvious way. Spectra taken of that supergiant revealed the lines shifting back and forth with a period of about 5 6/10 days, which is the signature of orbital motion around an unseen partner. From the period and the size of the velocity swing, one can compute a single combination of masses, and that combination sets a floor beneath the companion's mass once the visible star's own mass is estimated and the unknown tilt of the orbit is allowed for. Spectral type and luminosity put the supergiant at 20 solar masses or thereabouts, and on that basis the dark companion came out heavier than any neutron star could be. Estimates in the 1970s clustered around 6 solar masses. Later work, with the distance measured by radio interferometry, has raised the figure considerably. 2 absences strengthened the case as much as the mass estimate did. Matter accumulating on the surface of a neutron star eventually ignites in thermonuclear flashes that show up as short, sharp bursts, and Cygnus X1 has never produced them, nor does it pulse. A body with no surface for gas to settle on, and no magnetic field anchored in solid matter, would be expected to behave exactly in this way, radiating instead from hot gas swirling in toward a horizon and varying erratically as that gas shifts about. The source does alternate between 2 broad states, one dimmer with a harder spectrum and one brighter and softer, and the transitions between them are gradual and irregular rather than clock-like. Accretion accounts for the energy without difficulty. The supergiant sheds a thick wind, part of which is captured and drawn into a flattened orbiting flow, and friction within that flow carries matter gradually inward while heating it to temperatures of millions of degrees, at which gas radiates chiefly in X-rays. Efficiency is the point of the argument. Hydrogen fusing into helium liberates under 1% of the mass involved as energy, whereas material spiraling down close to a compact object can give up several percent of its mass in radiation before crossing the boundary, which makes accretion the most productive process available to a star-sized system. Doubt lingered for some years, and reasonably so, since the mass estimate rested on the properties of the visible star, and alternative arrangements involving a third, hidden component were proposed to keep the dark object below the neutron star limit. Confidence accumulated as further systems turned up in which the reasoning was cleaner. A transient in Monoceros flared brightly in 1975 and then faded away over months, leaving behind a faint, low-mass companion whose orbit could be traced without competition from the glare of a supergiant, and the mass it implied was harder to argue with. Another candidate was identified in the Large Magellanic Cloud, at a known distance, which removed one of the standing uncertainties. Instrumentation kept pace. Grazing incidence mirrors, in which X-rays reflect at shallow angles off nested surfaces, allowed genuine images to be formed rather than counts accumulated behind a collimator, and the observatory that carried the first such telescope of consequence into orbit at the end of the 1970s located thousands of sources with arc-second precision. Stephen Hawking, who had entered a wager in the mid-1970s against Cygnus X, one harboring a black hole, conceded it around 1990. By then, the phrasing in the literature had drifted from candidate toward identification, and a slowly lengthening list of similar binaries had begun to describe a population rather than a single peculiar case. Radio astronomy grew out of wartime electronics, and in the decade after the war groups in England and Australia began sweeping the sky with aerials assembled from surplus parts, finding discrete sources of radio emission that did not correspond to anything conspicuous in the optical catalogues. The positions were coarse at first, uncertain by many minutes of arc, which made identification a matter of guesswork among the faint objects crowded into each error box. A turning point came in 1954, when Walter Baade and Rudolf Minkowski matched the strong source in Cygnus to a faint, disturbed galaxy far outside the Milky Way, whose spectrum showed a substantial redshift. The radio output of that single object exceeded, by a wide margin, anything the local stellar population could plausibly generate, and the question of what powered it was left open. By the end of the 1950s, interferometers with baselines of hundreds of meters had tightened positions enough for systematic optical follow-up, and the third catalogue compiled at Cambridge supplied the working list. Several entries proved unhelpful in an interesting way. Thomas Matthews and Alan Sandage found that the source, listed as 3C48, coincided not with a smudge of galaxy light, but with something that looked like a faint blue star, apparently a point of light, whose spectrum contained broad emission features matching no laboratory element in the expected places. Its output flickered slightly from year to year, which stars of that color were not supposed to do. Similar coincidences accumulated, and for a few years the objects were filed provisionally under headings such as radio stars, a label nobody defended with much conviction. During 1962, Cyril Hazard and his collaborators used the Moon to solve the positional problem for one of them. The source 3C273 lay along a path the lunar limb would cross, and by recording the exact moments at which its radio signal vanished and returned, using the large dish at Parkes in New South Wales, they fixed its coordinates to a fraction of an arcsecond and resolved it into two components, one compact and one drawn out along a thin feature that pointed away from the first. The optical counterpart was a 13th magnitude object with a faint spike of light extending from it in the same direction, which had been photographed for years without anyone attaching significance to it. Martin Schmidt, working with a spectrum of that object taken at Palomar, spent weeks on its unruly emission lines before noticing that 4 of them formed the familiar hydrogen sequence, shifted uniformly toward longer wavelengths by about 16%. Jesse Greenstein and Matthews soon applied the same recognition to 3C48 and arrived at a shift near 37%. If those displacements arose from cosmic expansion, as the shifts of ordinary galaxies did, the objects sat hundreds of millions of light-years away, and their apparent faintness translated into an output tens or hundreds of times that of an entire galaxy of stars, emerging from something that no telescope could resolve into an extended shape. Nomenclature caught up gradually. Quasi-stellar radio source was the careful phrase, contracted in print during the middle 1960s to quasar, and as surveys deepened, it became clear that most such objects are weak radio emitters, so that the radio detections had merely provided the first accidental route to a much larger population. Their spectra shared a general character: broad emission lines implying gas moving at thousands of kilometers per second, a continuum far bluer than starlight, and in many cases absorption features imprinted by intervening material along the line of sight. 2 properties made the energy problem acute rather than merely puzzling. The output of several quasars varied appreciably over months, and in some cases weeks, which limits the size of the emitting region, since a source cannot brighten coherently across a distance greater than light can traverse in the time the change takes. That argument compressed the engine to something of the order of the solar system, or smaller. Meanwhile, the integrated energy released over a plausible lifetime came out larger than the rest mass of many millions of suns could supply through nuclear fusion, which converts only about 0.7% of the mass of hydrogen into radiation on the way to helium. An answer came from gravity, put forward independently in 1964 by Edwin Salpeter in the United States, and Yakov Zeldovich in the Soviet Union. Matter falling toward a collapsed object of millions or billions of solar masses gives up a substantial fraction of its rest energy before crossing the horizon, perhaps a tenth of it, more than an order of magnitude better than fusion, and the release happens in a region only a few times the gravitational radius across. Infalling gas carrying angular momentum cannot drop straight in. It settles into a flattened disk, where friction between neighboring rings transports angular momentum outward, lets material spiral slowly inward, and heats the inner disk to temperatures that radiate in the ultraviolet and in X-rays. Radiation pressure supplied a second line of reasoning, one that constrains mass from luminosity alone. Light streaming outward pushes on ionized gas, and when the outward push balances the inward pull, accretion chokes itself off. The limiting luminosity is proportional to the mass of the central object. Turning the relation around, the observed outputs of quasars require masses of at least many tens of millions of suns, and for the most luminous examples, a good deal more. The same relation sets a characteristic growth time, since a hole feeding at its limit can double its mass in a few tens of millions of years, which allows a modest seed to reach quasar proportions well within the age of the universe. Donald Lyndon Bell drew the natural consequence in 1969. If quasars were common in the early universe, and are scarce now, the collapsed objects that powered them have not gone anywhere. They should sit, starved of fuel, and therefore quiet, in the centers of ordinary galaxies nearby, including Andromeda and our own. He worked out the expected spectrum of a viscous accretion disk in some detail, and a few years later, Nikolai Shakura and Rashid Sunyaev published the formalism that became standard for such disks, parametrizing the unknown viscosity by a single coefficient and predicting how brightness and temperature should scale with radius and with feeding rate. Jets formed the third strand of evidence, and the oldest observation of one long predated any theory to explain it. Heber Curtis, photographing nebulae at the Lick Observatory in 1918, described a curious straight ray emerging from the nucleus of the galaxy in Virgo, now catalogued as M87. Radio maps of the 1960s and 70s revealed the general pattern: twin lobes straddling a galaxy at distances of hundreds of thousands of light-years, fed by narrow beams traceable back to an unresolved core. Very long baseline interferometry, linking telescopes on separate continents, tracked knots within those beams that appeared to move across the sky faster than light, an illusion produced when material traveling close to light speed heads nearly toward the observer, as Martin Rees had shown it would. Explanations for the beams themselves invoked magnetic fields anchored in the disk or threading the rotating hole, with Roger Blanford and Roman Znayak describing in 1977 how such fields could tap the spin energy of the hole and carry it outward electromagnetically. Seifert galaxies, catalogued by Carl Seifert in 1943 for their unusually luminous nuclei and broad emission lines, came to be read as the same phenomenon at lower power, and radio galaxies as the same engine seen through more obscuring material or from a different angle. What had begun as several unrelated curiosities settled into one family, distinguished by accretion rate, by orientation, and by how much dust lay along the sightline. Counting quasars by redshift showed their numbers rising steeply toward earlier epochs and falling away since, a history of galactic nuclei that were fed generously when gas was plentiful and have since subsided. Objections to the cosmological reading of the redshifts persisted for 2 decades, argued most persistently by Holt and Arp, who assembled apparent associations between high redshift quasars and low redshift galaxies. The case for distance strengthened as imaging improved and faint host galaxies were resolved around quasars, with redshifts matching those of the nuclei they surrounded, and as absorption lines from intervening clouds confirmed the long paths the light had traveled. What remained was a proposition about the local universe that could, in principle, be tested directly rather than inferred from luminosity, that a heavy collapsed object of the required kind sits quietly at the center of the galaxy in which we live. Toward the constellation Sagittarius, the band of the Milky Way thickens into crowded star clouds cut by dark lanes of dust, and behind those lanes, at a distance of roughly 26,000 light-years, lies the middle of the galaxy we inhabit. Visible light from that direction is almost entirely absorbed and scattered before it reaches us, dimmed by something like 30 magnitudes, which is to say, by a factor of about 1,000,000 million. No optical telescope, however large, can see through that curtain. At longer wavelengths, the dust becomes far less troublesome, and at 2 micrometers in the near infrared, the same sightline dims starlight only by a factor of 10 or 20, which is a loss an astronomer can work with. The history of what follows is therefore bound up with the slow development of infrared detectors and of radio receivers, and with the patience of people willing to return to the same small patch of sky for decades. Radio evidence came first. Karl Jansky, testing shortwave reception for a telephone company in New Jersey, reported in the early 1930s a persistent hiss that rose and fell with the sidereal day, and was strongest when his antenna pointed toward Sagittarius. As radio surveys grew more capable, that broad glow resolved into structure, and within the structure sat a bright complex catalogued as Sagittarius A, itself composed of an expanding shell of debris and a region of ionized gas arranged in curving filaments. In 1974, using a radio interferometer in the United States, Bruce Balick and Robert Brown found within that region a very compact source, unresolved at their resolution and quite unlike anything else nearby. The name Sagittarius A star was attached to it some years later, the asterisk borrowed from the notation physicists use for an excited atom. Compactness alone proved little. A small radio source could be many things, and the more interesting question was how much mass sat at the middle of the galaxy and how tightly it was gathered. Through the late 1970s and the 1980s, spectroscopy of ionized neon and of hydrogen in the innermost light years gave the first dynamical answers. Since the widths and shifts of those emission lines record how fast the gas is moving, velocities of a few hundred kilometers per second, rising as the sight line moved inward, implied a concentration of mass well beyond what the visible stars could supply. Gas, however, is a poor test particle. It responds to stellar winds, to radiation pressure, to magnetic fields, and to collisions with other clouds, and any of these could mimic or mask the pull of gravity. Measurements of the stars themselves, averaged as a velocity dispersion, pointed the same way, but suffered from the difficulty of knowing how those stars were distributed along the line of sight. What the problem required was individual stars, resolved as separate points, tracked one by one. That demand ran directly into the atmosphere, which smears any point source into a blur roughly 1 arcsecond across on a typical night, while the region of interest is packed so densely that dozens of stars can crowd into such a blur. A partial escape had been known since the 1970s in the technique of speckle imaging, which exploits the fact that atmospheric turbulence changes slowly compared with a very short exposure. Take thousands of frames of 1/10 of a second or so, and each will show the field broken into a shifting pattern of sharp specklets rather than a smooth smudge. Shift and add those frames appropriately, and much of the telescope's theoretical sharpness can be recovered. Two groups set about applying this to the Galactic Center in the 1990s, working independently and, for a long while, competitively. Reinhard Genzel and colleagues at the Max Planck Institute for Extraterrestrial Physics used an infrared speckle camera on the New Technology Telescope in Chile, beginning in 1992. Andrea Ghez, at the University of California, Los Angeles, began observing in 1995 with one of the 10-meter Keck telescopes in Hawaii, whose larger aperture gave finer resolution at the same wavelength. Both teams built up catalogues of faint infrared sources within the central light year, measured their positions to a small fraction of the seeing disk, and then waited. After a few years, the positions had shifted measurably, and the shifts were large. Proper motions corresponding to speeds of hundreds, and in some cases more than 1,000 kilometers per second, far above anything expected from the ordinary stellar mass of the region. Speeds constrain mass, but curvature constrains its location. By the late 1990s, the tracks of the fastest stars had begun to bend, and the accelerations, small as they were, all pointed toward a common focus within a few thousandths of an arcsecond of the compact radio source. The measurements had thus moved from statistics about a swarm to geometry about a point. Improvements in instrumentation arrived at the same time, as adaptive optics replaced speckle work, a deformable mirror driven by sensors reading the distortion of a bright reference star or of an artificial spot produced by a laser tuned to sodium atoms high in the atmosphere, corrected the wavefront in real time and delivered steady, sharp images rather than reconstructed ones. Astrometric precision improved by roughly an order of magnitude, and spectrographs on the same instruments began supplying radial velocities to complement the sideways motions. One star carried more of the argument than any other. Catalogued as S2 by the European group and S0-2 by the American one, it follows a markedly elongated ellipse with a period of about 16 years, which is short enough for a working astronomer to watch it close. Its closest approach, reached in 2002 and again in 2018, brings it within something like 120 times the Earth-Sun distance of the focus, about 17 light hours, and there it sweeps through at nearly 8,000 kilometers per second, some 2.5% of the speed of light. By the early 2000s, both teams had followed the star through a full circuit and published closed orbits, and the orbit of a single body around a central mass yields that mass by Kepler's third law with no need for assumptions about anything else. The number that emerged, refined over the following years and cross-checked against the orbits of a dozen other stars, is a little over 4 million times the mass of the Sun, confined within a region smaller than the orbits of the outer planets of our own system. That combination is what makes the result decisive. A cluster of ordinary stars or stellar remnants of such density could not last. Its members would collide, scatter one another away, and evaporate the cluster on a timescale short compared with the age of the galaxy. Radio interferometry supplied a further squeeze, showing the compact source to be no larger than tens of micro-arcseconds across, and tracking its position over years showed it essentially motionless with respect to the dynamical focus, apart from the drift expected from our own sun's orbital motion. A light object jostled by neighbors would wander. This one does not, which means it carries the mass rather than merely marking its place. Refinement continued into the era of interferometry across a single mountaintop. The gravity instrument, which combines the light of the 4 large telescopes of the Very Large Telescope Array to synthesize a much wider effective aperture, brought astrometric precision to a level where relativistic effects in the orbit could be looked for directly. During the pericenter passage of 2018, the expected shift of the star's spectral lines toward the red, arising both from its speed and from the depth of the potential well it was climbing out of, was measured and found to match prediction. 2 years later, the accumulated data showed the orbit slowly turning in its own plane, the ellipse failing to close on itself, and tracing instead a rosette at the rate general relativity gives for a body in that geometry. The same source flickers in the infrared and in X-rays on timescales of minutes to an hour, consistent with an emitting region only a few horizon radii across, and it does so at a luminosity extraordinarily low for its mass, a nucleus fed by the barest trickle of gas and quiet by the standards of its distant, brighter relatives. The Nobel Prize in Physics for the year 2020 recognized this work, one half to Roger Penrose for the theory of gravitational collapse, and the other half divided between Genzel and Ghez for the object at the heart of the Milky Way. Waves in the geometry itself were part of the theory almost from the moment the field equations were written down. Einstein worked out, within a few years of completing general relativity, that a mass distribution changing shape in the right way should send out disturbances in the curvature of spacetime, traveling at the speed of light and carrying energy away from their source. The results sat uneasily for decades. Because general relativity allows the observer to choose coordinates freely, a ripple in the coordinates can look like a ripple in space, and much of the argument through the 1930s, 40s and 50s turned on whether these waves were physical at all or merely an artifact of bookkeeping. The question was settled in favor of physical reality by arguments showing that a passing wave would do work on freely suspended masses, moving them relative to one another in a measurable way, and by the demonstration that the waves carried energy off in a form the source could feel as a loss. Confirmation arrived first without any detector of waves at all. A pulsar found in the mid-1970s in orbit around another compact star provided a clock of extraordinary regularity moving through a strong gravitational field, and the timing of its pulses gave the orbital period to many decimal places. That period was shrinking, year on year, by a fraction of a second per year, and the rate of shrinkage matched what the quadrupole formula predicted for a system losing energy to gravitational radiation. Joseph Taylor and Russell Hulse received the Nobel Prize for the discovery in 1993. The orbit was decaying, exactly as though invisible waves were streaming out of it. Catching those waves as they arrived was a far harder proposition. Early attempts used massive aluminium cylinders instrumented to ring at a particular frequency, the idea being that a passing wave would set the bar vibrating. The claimed detections of the late 1960s were not reproduced elsewhere, and the sensitivity of such resonant masses fell short by many orders of magnitude. A different approach came out of laser interferometry. Hang two pairs of mirrors at the ends of two long perpendicular arms, split a laser beam between the arms, recombine the returning light, and watch the interference pattern. A wave passing through will lengthen one arm and shorten the other, shifting the fringes. A study written at MIT in the early 1970s by Rainer Weiss set out the noise sources such an instrument would face, from seismic ground motion to the thermal jitter of the mirrors to the random arrival statistics of the photons themselves, and estimated what each would cost in sensitivity. Ronald Draver pursued related techniques in Glasgow and later in California. Kip Thorne provided the theoretical case for what might be detectable, and Barry Barish later reorganized the project on the scale a working observatory required. Two facilities were built in the United States, one in eastern Washington state and one in Louisiana, each with arms 4 kilometers long held under vacuum, the light folded back and forth hundreds of times within optical cavities so that its effective path was longer still. Separating the sites by 3,000 kilometers gave the essential test. A genuine wave sweeps through both within the 10 milliseconds light needs to cross that distance, while local disturbances, a truck on a road or a storm on a coast, do not. A comparable instrument with 3-kilometer arms was built near Pisa, and a smaller one in Germany served as a proving ground for techniques. The mirrors are cylinders of fused silica weighing tens of kilograms, suspended on fibers from cascaded pendulums, polished so that they scatter almost nothing. An initial phase of operation ran through the 2000s and recorded no signal, which had been the expectation. It established that instruments of this design could be run at their design noise for long stretches. The upgrade that followed roughly tripled the reach of the detectors and, since the volume of space surveyed grows as the cube of the distance, multiplied by something like a factor of 27, the rate of events they might encounter. Observations with the improved instruments began in September of 2015. On the 14th of that month, before the formal run had even started, both sites recorded the same brief disturbance. Louisiana about 7 milliseconds ahead of Washington. The signal rose in frequency from around 35 to around 250 cycles per second while growing in amplitude, then cut off sharply and rang down. Whole duration in the sensitive band about 0.2 of a second. Matching the waveform against calculated templates gave two black holes of roughly 36 and 29 solar masses spiraling together and merging into one of about 62, with the missing 3 solar masses carried off as radiation at a distance of something over 1 billion light-years. Peak strain at the detectors was near 1 part in 10 to the 21st, which over 4 kilometers of arm amounts to a displacement of a few thousandths of the width of a proton. Announcement came the following February, after months spent checking the instruments against every mundane explanation available. What made the interpretation firm was the shape of the late signal. Objects orbiting each other several tens of times per second, with tens of solar masses apiece, must be smaller than a few hundred kilometers across, which excludes ordinary stars and white dwarfs. The masses exceed anything a neutron star can hold. After the merger, the waveform showed the brief ringing of a single distorted object. settling down, at the frequency and damping rate general relativity gives for a spinning black hole of that mass. The prize in physics for 2017 went to Weiss, Barish, and Thorne. Detections became routine within a few years. The addition of the Italian instrument in the summer of 2017 allowed positions on the sky to be triangulated from 3 sites. And in August of that year, a signal of quite different character, lasting 100 seconds and rising to higher frequencies, was followed within 2 seconds by a short gamma-ray burst and, over the following days, by an optical and infrared glow found in a galaxy 130 million light-years away. That was 2 neutron stars, not black holes, and it tied the whole enterprise to conventional astronomy. By the end of the 3rd observing run, the catalogue held roughly 90 events, most of them black hole pairs, including systems more massive than stellar evolution had comfortably predicted. A detector built underground in Japan, cooled to reduce thermal noise, joined the network, and squeezed light was introduced at the interferometer outputs to push below the shot noise limit. Seeing a black hole directly was a separate problem with a separate solution. Resolving a horizon means resolving an angle of tens of micro-arc seconds, about what a small fruit on the surface of the moon would subtend, and that requires either an impossibly large telescope or an array of small ones spread across a continent-sized baseline. Their signals combined after the fact. Very long baseline interferometry had done this for decades at centimeter wavelengths. The horizon problem demanded roughly a millimeter, where the atmosphere is troublesome and the electronics unforgiving. In April of 2017, 8 facilities at 6 geographic sites observed together at a wavelength near 1 1/3 millimeters. The large arrays in the Chilean desert, a telescope in Mexico, 1 in Arizona, 1 in the Spanish Sierra, 2 on Mauna Kea, and 1 at the South Pole. Each recorded raw voltages onto banks of hard drives, timestamped against hydrogen maser clocks, generating petabytes of data that no network could carry. The drives were flown to correlators in Massachusetts and in Bonn, where the streams were aligned and interfered. The South Pole shipment had to wait for the end of the austral winter. 4 teams then worked separately, with different algorithms and deliberate isolation from one another, before comparing results. The image, published in April of 2019, showed a ring of emission about 42 micro-arc seconds across, brighter along its lower edge, surrounding a darker center. In the galaxy Messier, 87 some 55 million light-years away, ring size implied a mass near 6.5 billion suns, consistent with the larger of 2 earlier stellar dynamical estimates. Asymmetry in brightness followed from gas moving toward us on one side. Its light beamed forward by its motion. Later analysis of the polarized light traced ordered magnetic fields, threading the flow near the base of that galaxy's jet. 3 years afterward, the same collaboration released a picture of the source at the center of our own galaxy. Harder to make because gas there completes an orbit in minutes, and the scene changes while the Earth turns beneath it. Averaging over that flicker yielded a ring near 52 micro-arc seconds, which for a distance of 26,000 light-years corresponds to a mass in close agreement with the figure the stellar orbits had already given, arrived at by wholly independent means. Nothing in the classical theory permits a horizon to grow smaller. A theorem proved at the start of the 1970s established that the combined area of event horizons in any process allowed by general relativity can only hold steady or increase, so that two holes which merge leave behind a surface larger than the sum of the two that went in, and every parcel of matter that crosses inward enlarges the boundary it crossed. Resemblance to the behavior of entropy in ordinary thermodynamics was noticed almost immediately, and for a while treated as a coincidence of form. Since a collapsed object in the classical description has no temperature whatever, and something without a temperature cannot come into thermal balance with anything else. A doctoral student working at Princeton took the parallel literally, proposing that a horizon carries entropy in proportion to its area measured in units, built from the gravitational constant, the speed of light, and Planck's constant, and that the second law of thermodynamics survives the swallowing of a hot gas only because the growth of the horizon more than makes up for the entropy removed from the outside world. Established relativists objected, among them the author of the area theorem, on the reasonable ground that entropy without temperature made no sense. A set of laws set out in 1973 by three researchers working together sharpened the correspondence rather than dissolving it, with the surface gravity, which is constant everywhere on a stationary horizon, standing in the position occupied by temperature, and the mass standing where internal energy stands. The calculation that changed the standing of the analogy was published in 1974, and it began as an attempt to show that the entropy proposal could not be right. Quantum fields were treated as ripples propagating on the curved geometry of a star that collapses, with the gravity itself left classical, and the state of those fields was compared long before the collapse with the state seen long after it. The comparison did not come out empty. An observer far away, in a region that had been quiet before the star fell in, would find a steady outward flux with a thermal spectrum, characterized by a single temperature set by the surface gravity of the resulting horizon, and the constant relating entropy to area fell out at 1/4. Descriptions of the process in terms of particle pairs appearing near the horizon, one member falling in and the other escaping, are useful as a picture and misleading if pressed. The derivation says something less pictorial and more precise. What counts as empty space depends on the observer and on the geometry. The notion of vacuum appropriate before the collapse and the notion appropriate afterwards are not the same notion, and modes that begin as vacuum arrive at a distant detector populated with quanta. Energy carried away is drawn from the mass of the whole, which therefore declines, and the horizon shrinks in exact opposition to the classical theorem, whose assumptions quietly exclude the negative energy densities that quantum fields permit. Temperature in this scheme runs inversely with mass, which puts astrophysical objects at the cold extreme of everything known. A hole of one solar mass sits at roughly 60 billionths of a degree above absolute zero, and the radiation it produces is so weak that no conceivable instrument could register it across any distance. The object at the heart of Messier, 87, with some billions of solar masses behind its horizon, is colder again by a comparable factor, and its emission consists almost entirely of photons and gravitons of enormous wavelength. Since the temperature lies far below the threshold at which particles with mass could be produced, the spectrum is not perfectly thermal either, because the curved geometry outside the horizon scatters part of the outgoing radiation back, and the resulting filtering is folded into the calculation as a set of transmission factors. cooling of this kind cannot begin while the surroundings are warmer than the whole, and the sky at present is warmer everywhere. Relic radiation from the early universe fills space at a little under 3 degrees above absolute zero, so every black hole in existence absorbs far more energy from that bath than it gives back, and all of them are gaining mass rather than losing it. Continued expansion lowers the background temperature in proportion to the stretching of wavelengths, and the crossover for a stellar mass object requires that bath to fall by a factor of tens of millions. With the expansion accelerating, that dilution takes a span long compared with the present age of the universe, though negligible against what follows. Mass loss, once it does begin, proceeds at a rate that rises steeply as the object diminishes, since a smaller hole is hotter and radiates from a surface whose temperature climbs faster than its area falls. Working the arithmetic through gives a lifetime that scales as the cube of the mass, and for a body of 1 solar mass, the figure comes out near 10 to the power of 67 years, a 1, followed by 67 zeros. The largest known holes, weighing billions of suns, require something closer to 10 to the power of 94 or 100 years. These spans are not measured against anything. The age of the universe so far, some 14 billion years, does not register on such a scale as even a rounding error. Holes far smaller than any star would run much faster and could only have formed under conditions that no longer exist. Density fluctuations in the first fraction of a second after the expansion began might, if sharp enough, have collapsed directly into horizons of almost any mass, and objects of a few 100 million tons, with radii comparable to that of a proton, would be reaching the end of their lives about now. Their last stages would appear as bursts of gamma rays with a distinctive rising spectrum, and searchers through the records of gamma ray observatories have turned up no such events, which sets limits on how many primordial holes of that size the early universe produced. Toward the end of any evaporation, the description grows uncertain. Heat capacity is negative throughout, so the loss of mass raises the temperature, which raises the emission, which accelerates the loss, and the final moments compress an increasing share of the total energy into a decreasing interval. Once the remaining mass approaches the scale at which quantum effects in gravity itself become important, the framework used to derive the radiation no longer applies, since it assumed a fixed classical geometry with quantum fields upon it. Whether the object disappears entirely, leaves a stable remnant, or ends in some way not yet described, is among the open questions that a full theory of quantum gravity would settle. A deeper difficulty was raised by the author of the result himself, 2 years after publishing it. Radiation with a purely thermal spectrum carries no detail about what fell in, depending only on mass, spin, and charge. So if a hole forms from a collapsing library and evaporates into thermal quanta, the correlations that quantum mechanics normally preserves have gone missing. Ordinary quantum evolution is reversible in principle, and this process appears not to be. Decades of argument followed, with proposals that the information leaks out in subtle correlations between the emitted quanta, or that it resides on the horizon in a form described by a theory living on a boundary surface, and the matter is not settled. Set against these timescales, the eras that precede them look brief. Star formation will wind down as galaxies exhaust the gas available to them, and the last low-mass stars will burn steadily for something like tens of trillions of years before fading into cold, degenerate remnants. Encounters between those remnants will gradually disperse the galaxies themselves over spans nearer 10 to the power of 20 years, flinging most objects into intergalactic space and sinking a minority toward the centers. Whether protons' decay remains unknown, with experiments having watched large tanks of water for years and found no such event, which places any lifetime beyond 10 to the power of 34 years, and leaves open the possibility that ordinary matter persists far longer. Through all of that, horizons remain, growing at first on the radiation around them, then shrinking with immeasurable patience once the sky has cooled beneath them. They outlast stars by scores of orders of magnitude, and by the arithmetic now understood, they are the last organized structures the universe contains. What follows their departure is a thin and cooling gas of photons and light particles, spread through a space still expanding, at temperatures approaching, but never reaching zero. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well, and see you very soon.